This is section 2.6. This is called related rates. This is probably up to date will be the most difficult at first things that we do. So the real important part is trying to understand why everything is working the way it is and not trying to memorize, because with related rates it's a very nice application to what we've been doing with derivatives. So if you can understand what that application is, then it actually becomes pretty easy. So you can read up here, it says, we have dealt with finding derivatives implicitly. So we did the implicit differentiation with respect to the variable x. What we're going to now do is we're going to talk about using the same method to find rates of change, which is still a derivative, when we have multiple variables, but we're going to be doing everything with respect to time. So for example, when I say that you're driving on a road, like what we were working on in class with our velocity, our acceleration, and our position, everything that we do there is with respect to time. And the same thing is true when we're talking about related rates, because now we're talking about objects, usually the area of something or the volume of something. So if you look at this cone right here, we're going to look right into this example. So everything is going to be with respect to time, but the formula will not have a t in it. So that's what makes it really confusing, and I'm going to explain that a little bit as we move through this. It says water is draining out of the cones above. The volume, radius, and height of the cone are all functions of time. In other words, what it's saying is the volume will change. The volume of the cone will change with respect to time. The radius of the cone will change with respect to time, and the height of the cone will change with respect to time. So if you look at this, this is when it was full, and then now you can see that it's starting to go down. Well, the thing is the volume has changed because there's less water in there. The radius has changed because there's less water in there, and the height has changed, and then again it keeps changing until all the water is gone. So when we talk about derivatives and we said, okay, what is a derivative? And many of you will say, well, it's a rate of change or it's a slope. Well, that is true. So rate of change is also what we're dealing with here, but what we've done before is if you notice that we have v equals 1/3 pi r squared h. What we need to understand is before we would say if I take the derivative of v, that would be the same thing as saying v prime. And that's fine in this case, v prime, but what we're going to do is we're going to change it to be, instead of v prime, we're going to do dv. And before we would say, okay, if I have y equals, we would say either y prime or we would say dy dx. In this case, it's going to be a little bit different because here we are finding the rate of y with respect to x. Here we're finding the rate of v, or the change of v, dv, and instead of it being a variable that's in our equation, it's going to be with respect to time. So it's going to be dv dt. Okay, so that's the derivative of v with respect to time. So that's what we're going to end up finding here, and it's going to be the derivative of our volume. Now, here's this. We're starting off with a really difficult problem, but that's okay. We have two variables here. We have an r, radius, and we have h, height. And notice they are being multiplied by each other. So you need to make sure, okay, if something's being multiplied by each other, we still cannot abandon our regular rules of taking derivatives, which is the product rule here. So our f is going to be the first portion of it, the 1/3 pi r squared. And our g is going to be the second portion of it, just the h. The difference is now, remember what we just said. Everything is being derived with respect to t. So now it's going to look exactly the same as it did when we did our implicit differentiation. When we took the derivative of, say, y squared, when we took the derivative of that, we ended up with 2 times y, and then we would have a y prime, which is the same thing as writing 2 times y times dy dx. The same thing is going to happen here. The exact same thing. So when I do my f prime, it's going to look like 2 times 1/3 is 2/3. And then we still have our pi, and then we have our r. That's the derivative portion, but then we still need to multiply by r prime, so to speak, which is going to be dr dt. Okay, derivative of r with respect to t. That's the implicit part of this. So nothing has changed. We're just doing everything implicitly because there's no t to take a derivative of. Now we go to g prime. So g is our h. The derivative of h is just 1, so it's 1 times, and then again we have to do the same thing, dh dt. So now when we write out our derivative, it's just going to be the product rule, which will be f prime times g, so it'll be 2/3 pi times r times dr dt, and then don't forget to multiply by our g, which is h, plus, now we do our g prime, times our f. So I'm just going to leave the f first, so f is 1/3 pi r squared, and then multiply it by our g prime, which is dh dt. So now when you look at this, I know this seems like a pretty crazy formula here, but let me explain how this works and why it's going to work the way it is. What we said is the dv dt is the rate at which the volume is changing with respect to time. The same thing is true about the dr dt and the dh dt. The dr dt is how the radius is changing with respect to time, and dh dt is how the height is changing with respect to time. So what's going to happen is we can know what the original, if we know what the radius of our cone is, and we know at the rate at which the radius is changing, and we know the rate at which the height is changing, and we know the height of the cone, we can actually determine the rate at which the volume is going to change based on what the rates of these are. So that's kind of the idea, is we're going to find the derivative so we can figure out what the rate of changes of an area or a volume. Okay, so there's our formula. So now let's kind of dig into this a little bit deeper, but with an easier problem. It says a rock is tossed into a lake, and the splash of the water causes a perfect circular ripples. So we're talking about circles here. So therefore, we're dealing with the formula A equals pi times r times square, pi times r squared. So now it says the radius of the outer ripple is increasing at a constant rate of 2 feet per second. We'll talk about that in a minute. When the actual radius of the outer ripple is 6 feet, so they're giving us two different things here, and we're going to talk about what those represent. It says at what rate is the total area changing? So as soon as you see at the rate, the total area, you should be thinking we need dA dt, which means we're just going to take the derivative of this. 2 times pi times r, but don't forget, we need to add in there a dr dt. We're taking this derivative implicitly because it's with respect to time, not with respect to r. So now let's look at the available things that we have. We're trying to find this. So what are we given? We're given our radius. So that our radius is going to be 6. Are we given the rate at which our radius is changing? Yes. It's increasing at a constant rate of 2 feet per second. So our dr dt is just 2. And then we have the 2 pi out front. So we multiply all those together, and we get dA dt equals 75.398, and this is feet per second. That's the rate, feet squared per second. That's the rate at which the area is changing. So area is feet squared, and it's per second. Okay, so 75.398 feet squared per second. Okay, but that's basically all we're doing, is we're taking a derivative, plugging in what they give us, and trying to find whatever's missing. Okay, but make sure that when you're taking the derivative, you're doing it implicitly with every variable with respect to t. So I want you to try this one on your own. The volume of a sphere is given to you, and you're going to try and find the rate at which the volume is changing. Okay, so try this one on your own. Hit pause if you need to. Otherwise, the video will stop on its own, and take the quiz or do the problem, and then we'll see how you do. All right, so when you did this, you should have gotten a derivative, dv dt. You multiply 3 by the 4 to get 12 over 3, which is 4. Pi r squared, lowered the power by 1, and then don't forget we need a dr dt at the end. Then we just plug in what we know. We know the radius is 2 feet. We know that the radius is changing at 0.09, so that's what we put in for dr dt. And then we just evaluate, and we get that our dv dt is 4.524 feet cubed per minute, because we're talking about a volume. Okay, so hopefully this makes sense. We are going to work on this in class, so make sure you bring questions there. So, well, I'll see you then.